All right, hello students. So I am trying something a little bit different. Well, welcome to class. I'll start there. And so I've converted every page in the book as best I could with my cell phone and photographs into this slide presentation. And I'm making this video as far as instruction goes. And take a look in Google Classroom to see the assignment associated with the instruction. So this is all coming out of the first section of Chapter 10, which is our introduction, kind of, to quadratic equations and functions, specifically exploring quadratic graphs. So we've got some key vocabulary, and a lot of it's going to be new. Some of it's going to be familiar, like maximum and minimum. We're going to see how that relates specifically to the graph of a quadratic equation, which happens to be a parabola. And anyway, since we're in this environment, what we're going to do is I'm going to create a separate assignment strictly for vocabulary, and it will have all of these words in it. I'm going to have a slide, Google slide, created in such a way that every student will get a copy when I assign it, and that'll be your copy. There'll be instructions there for that. Anyway, just take a look at some of the vocabulary that is going to get introduced during this chapter. This is vocabulary for the chapter, not just this section. However, in this section, we're going to be focusing on the axis of symmetry, maximum, minimum, parabola, quadratic equation, quadratic function, quadratic parent function, and vertex. All right, the others will come as time moves on. All right, so we're just going to go through a little bit of vocabulary here, and then like we do in class, we're going to go through the quick checks, give yourself the opportunity to try something out and see what the answer is for those particular problems. So right now, quadratic function, basically y equals x squared. That's going to be the parent function. But I want you to think back to polynomials. We just finished that, right? We are talking about second degree polynomials. It might be a trinomial, it might be a binomial, it might just be a monomial. But we're looking at it being a second degree. And of course, a cannot be 0. If a were 0 in this scenario, we wouldn't have an x squared. So we need an x squared there. All right. So quadratic function is going to be a relation of y to our second degree polynomial. So we have not been working with equations for a while now, in the previous chapter especially. So now we are. So once we introduce y into the equation, pardon the pun, we're going to end up graphing and having coordinate pairs and solutions, and all of that you thought you left behind with linear equations, it's all coming back. So this form, a x squared plus bx plus c, is going to be the standard form of the quadratic function. So again, like in polynomial standard form, sorry if there was a hiccup there. I had to edit out a text message that came on the screen. Anyway, so we are here, and oh, I've got a pointer. I forgot I've got that. So function. That means we've got a y involved. All right, so here are some examples. Y equals 5x squared. That's going to be a quadratic function. X squared plus 7 is a quadratic function. And then here we have a trinomial, x squared minus x minus 3 equals y. So standard form of a quadratic function, quadratic function. Simplest quadratic function is a quadratic parent function, y equals x squared. All right, the graph of a quadratic function is going to be a U-shaped curve. That U-shaped curve can be very narrow and steep, or it can be very wide and flat, but that U-shaped curve is going to be called a parabola. All right, so if I click, is it? Yes, awesome. Love trying new stuff. It's always a experiment. Anyway, so you can fold a parabola so that the two sides match exactly. So there's an axis of symmetry, there's a line of symmetry, and in this case it's an axis. There's a line of symmetry when it comes to parabolas, and what's really helpful there is that if you can graph half of a parabola on one side of the axis of symmetry using symmetry and measurement of distance from the curve to the axis, you can graph points on the other side of the axis. So basically, if you can graph half of a parabola, you can graph the other half without having to do any additional hard calculations. All right, so the highest or lowest point on a parabola is called a vertex. If there's more than one vertex, the plural of vertex, is a vertex, is not a vertice, is vertices. Vertices? Yes, that's correct. Yes, it just sounds weird when you say it, right? So when we talk about vertices, we will be talking about a specific vertex of a parabola, which may be a minimum or a maximum. Now, This little rule here tells us that if a is positive or larger than 0, then the parabola is going to open upward, which means our vertex is going to be a minimum point. All right. If a is less than 0, meaning a is a negative number, then our parabola opens downward and our vertex is a maximum point. So here we've got a minimum point, a maximum point. Both of those are vertices, and the difference in how you're going to tell in the equation is the sign of a. Positive a, it's going to be a minimum and it's going to curve up. Negative a, it's going to be a maximum and curve down. All right, so here we go, identifying vertex. So when you look at a parabola that's graphed, you're going to look for the graph to swoop in, reach a point in which it does a U-turn and heads back the same direction it came. In this case, it's a negative direction. In this case, it's headed off from the vertex in a positive direction. So if you're already thinking, okay, if I'm looking at the equation for this, it's pointing up, that means A is positive. This graph is pointing or curving down, therefore A is negative. All right, that's not what the question's asking, but just something to keep in mind. All right, so the vertex, we're getting back into coordinate points, folks. So X is 1, Y is -2. That's going to be its minimum. Here, the vertex is X is -2, Y is +4. Therefore, this coordinate represents the maximum of the graph. So here's the quick check that you should have in your spiral. All right, take a look at these graphs. I would just sketch them in real quick, sketch them into your spiral. Again, an answer without a source of where the problem came from isn't really helpful, right? But instead, if you have your answer of the minimum and maximum for these two graphs accompanied with a sketched out graph, then it'll make more sense if you study it later. So for A, you are looking for the maximum. For B, you are looking for the minimum. Go ahead and put this on pause if you're checking your work. If you're not, then here we go. Here are the answers. So we have on the graph A, X is 4, Y is +3, and that is going to be a maximum. B, X is -3, Y is -3, and that is going to be a minimum. All right. We're going to learn later that the axis of symmetry, or it might have actually been addressed in the book, but either way, you need to know that the axis of symmetry does pass through the vertex of the parabola. All right. So let's take a look at example 2. So we are going to graph the basic function, almost the parent function, right? It's y equals x squared. However, we're going to start playing with the values of a and see if we can follow order of operations, right? Exponents first, then multiplication. So here in this case, y equals 1/2 x squared. We substitute in, so we're graphing by substituting and selecting variable values for x, right? So we can graph a quadratic. We're going to learn that there's different ways that you can graph a quadratic equation, but just like when you learned how to graph linear functions, it was just a pick an x, figure out what y is, and graph those points, then connect the dots, right? We're going to do the same thing here, and we're going to use the axis of symmetry, which passes through the vertex. All right. The cool thing about this setup, where we only have one term, right, where we only have ax squared, is that the vertex of this function, no matter what a is going to be the origin. It's just going to be the origin. So when x equals 0, y is going to equal 0, and that's going to be the vertex. If a is positive, it'll curve up. If a is negative, it'll curve down. But either way, our line of symmetry, or our axis, is going to be the y-axis. Axis of symmetry, excuse me. So here we go. We have 1/2 x squared. So we substitute in 0. Doesn't matter what's going on. The output's going to be 0 here, unless we're adding. In this case, we're not. So we have x is 0, y is 0. Here we're going to substitute x is 2. We need to make sure to square 2 first. So 2 squared is 4. 1/2 of 4 is 2. Therefore, we end up with the coordinates 2, 2. When x equals 4, 4 squared is going to be 16. 1/2 of 16 is going to be 8. We get 4, 8. So once we graph those points, we use the axis of symmetry and a little bit of measurement and say, hey, if this point exists on the right-hand side of the axis of symmetry and it is 2 units or 2 scaled units, in this case, those are each worth 2, So let's say 4 units away from the axis of symmetry, well, then there is an equivalent point on the other side, on the mirrored side of this parabola, and we can go out 4 units in this direction and graph this point. Same thing here. We have a point that is 2 units away from the axis on the positive direction. That means we have an opposite point in the negative direction, exactly 2 units away from the axis. So we can quickly graph that function. So here, quick check is saying make a table of values and graph the quadratic function f of x, f of x. Oh, f of x, what the heck? I thought it was y. Same thing, right? Function of x. So y is a function of x. So another way of writing it is as a function. So we can say a function of x is negative 2x squared, right? So this value is a function of x. Something's happening to x to give us this value. Just a quick reminder there. Imagine you've gone over it. So here, this says, oh, let me get this out of the way. And okay, go back, Vincent. How do I go back? Ooh, just like that. Make a table of values and graph the quadratic function f of x equals negative 2x squared. So you shouldn't be surprised that this is pointing down because a is negative, right? We also do not have any other values other than the monomial with a. So with that very first term, our squared term, so we know our vertex is going to be 0, 0. So what I did is I went ahead and for my table of values, I ignored the idea of the axis of symmetry and gave myself negative 2, negative 1, 0, 1, and 2 for x values because I want to show you, like literally in a table, that we have mirrored negative. Oh, this table's wrong. I'd have to fix that. No, it's not. No, it's not. Wait. No, it's not. My bad. So second guess yourself, right? To show you how it's basically the same point, just on the other side of the axis. All right, so when x is 0, y is 0, 0 squared times negative 2 is going to give me 0. Now when I put in 1, 1 squared is 1. 1 times negative 2 is negative 2. So that's when x equals 1. That's this value here. Y equals negative 2. Well, because it's a squared function, and this is why the axis of symmetry works, if I put in a negative 1, this negative 1 here, a negative times a negative is a positive. So we end up with the same value here that we're multiplying times negative 2, which is, of course, negative 2. So we end up with this point here, right? So let me get that banner at the bottom out of the way. And when I have x is positive 2, 2 squared is 4, negative 2 times 4 is negative 8. That's how we get this here. Now, if I'm just using the axis of symmetry, I'm looking at two scaled units to the right. So I do 2 scaled units to the left, and that would give me this point. Oops. But if I am looking at the table, I say, hey, wait a minute. If I put in negative 2 instead of positive 2, squaring it makes it basically the same thing as positive 2. And not even basically, just the same thing as positive 2. So I end up with the same exact answer. So that's why I end up with the same y value on the other side of the y-axis. So that's visual representation of the axis of symmetry using values in a table. All right, so your graph should look similar to that for quick check 2. Example 3. So now we're going to say, hey, wait a minute. We haven't, we're talking about whether it points up or whether it points down. We haven't really talked about what else we should be considering when looking at that a value. And here, when we talk about the widths of parabolas, that's where we get to talk about, hey, what exactly is that a value doing other than determining an upward curve or downward curve, right? So these are graphing calculator graphs of the following functions. And hopefully you're watching this video after going through the material yourself, because I'm just going to cut to the chase a little bit quicker than usual. What you're supposed to notice is that the closer you get to 0 for your a value, the flatter your curve, or the wider your curve gets. And actually, the closer we push this a value to 0, you know, 1/1,000th, if that was our a value is 1/1,000th, this would be a very flat curve, right? And as we push it to the limit of 0, we're pushing our curve so flat that it almost becomes a horizontal line. So the closer we get to 0, the closer our curve looks like a horizontal line. All right. However, once we start going the other way, away from 0, and it doesn't matter whether it's positive or negative, negative is just going to make it point down. It doesn't change the width. So whether it's positive or negative, the further we get away from 0, the more narrow our graph gets. All right. So as we push this number towards infinity, we start to approach the appearance of a vertical line. Isn't that interesting? As we push this towards 0, we get so flat it almost looks horizontal. As we push the a value towards infinity, we get a curve that almost looks like a vertical line. All right, just something to think about, kind of big picture. But generally, closer to 0, wider it is. Further away from 0, more steep or more narrow the curve is. So for quick check 3, I wish I could get that out of the way. Let's say I just have to stop moving. So for quick check 3, order the quadratic functions, y equals x squared. Order the quadratic functions from widest to narrowest. So widest, we need the smallest a. Narrowest, we need the largest a, absolute value-wise, so furthest away from 0. So if we're going to order these, the first one is going to be y equals 1/2 x squared. The second one is going to be y equals x squared. That's what's hiding behind this banner. And then the third one, the most narrow, is y equals -2x squared. Fantastic. All right, now we're moving on to adding another part of our quadratic equation. What is the deal with c, right? Ax squared plus bx plus c. We're going to focus on c. We'll get into b at x later. Right now we know that a, the sign of it determines pointing up or pointing down. Closer to 0, wider the curve. Furthest away from 0, more narrow the curve, right? So what does c do? C, looking at this example, I'm going to let you go over it on your own. Basically, what you're supposed to discover is that C represents a vertical shift or translation. Hopefully that word sounds familiar. A vertical translation of your graph. All right, which means the graph is not going to change shape if we keep a constant, if we keep a static and compare two different functions and only change C. Changing C will only change the vertical position. And actually, C is going to represent our y-intercept. And think about it. Back in linear equations, when x equals 0, right? Whenever we substituted 0 for x, that would tell us what our y-intercept is. Well, guess what? Same deal here with a quadratic. If I put in 0 for x, 0 squared times a is going to give me 0. So y is going to equal whatever c is. And even when we throw bx back in the mix, if x were 0, that means b, whatever it is, times 0 is going to go away as well. So no matter what, when we substitute in a 0 for x, we're going to get out c for y. Therefore, c is going to be our y-intercept, something to keep in mind. All right, so we're just talking about a vertical shift. And if the shape doesn't change, I wonder if these two curves would ever intersect. If they're the same curve, and one of them is just shifted vertically 3 units, in this case, 3 units, will they ever intersect? Hopefully, you see that the answer is no. They're basically, quote unquote, parallel quadratic functions. All right, they're going to have the same shape, and while towards infinity, they're going to get really, really close. They're never going to touch. All right, so let's address the question. So for these two graphs, if one equation has a +3 and the other one does not, what is the shift? You're going to see it's a vertical shift 3 units up. So the correct answer is A. All right, let's do your quick check. Quick check here. Graph these two functions. I recommend you go out to Desmos, or actually hand graph these. I'm sorry. You can go out and check it in desmos.com if you want, but hand graph these. If you have graph paper, awesome. If you don't, quick sketch will be fine. So graph the parent function y equals x squared, and graph the function y equals x squared minus 4. Compare the two graphs. All right, what you should end up with are two graphs that curve up in the positive direction. The second graph is going to be shifted down 4 units. All right, so you should have two graphs that look very similar to this, except for this is going to be graphed as that red curve there, and it's going to be a little bit wider because it's the parent function. And the second parabola is going to be shifted down 4 units, down because it's negative. Critical thinking, describe what positive and negative values of C do to the position of the vertex. So just write this out in a sentence or something similar, paraphrase it, that would be awesome. The C value translates the values of the let me rephrase. So due to the position, to the position of the vertex. Okay. So positive values of C move the vertex up the y-axis. Negative values of C move the vertex down the y-axis. It doesn't matter whether it's a minimum or a maximum. That direction will be the same. All right. Positive values of C will move it up the y-axis. Negative values of C will move it down the y-axis. All right. Awesome. Quick check 4. Last one, real world problem solving. Okay, so parabolas and quadratic equations describe movement caused by gravity, of course, ignoring air resistance, which you're going to get tired of hearing that over the next, forever when you're studying math. You got to ignore air resistance. You'll be in a class where you don't ignore air resistance and you try to factor it in, and you'll realize, oh shoot, that's why they always said ignore air resistance, right? But if you're trying to land something on another planet, don't ignore air resistance. Okay, so here we have this function. Height of an object can be described by taking -16 and multiplying it times the time that the object has been falling squared plus the original height of the object. So the height of the object is in feet, time is in seconds in this case. Therefore, the initial height of the object is in feet. So this is the function that is going to describe a falling object, right? This is negative because it's curving down, and we're describing height because something is falling. C is the y-intercept, or the initial value. It's also going to, because there is no bx here, this is going to help us find our vertex. So this is where everything begins, right? Initial value, just like the y-intercept for linear equations. We're talking initial value here. So suppose you see an eagle flying over a canyon. The eagle is 30 feet above the level of the canyon's edge when it drops a stick from its claws. Force of gravity causes the stick to fall towards the earth. Function h equals -16 t squared plus 30, because 30 is the initial height of the stick, gives the height of the stick h in feet after t seconds. Graph this quadratic function. This would be the graph of the quadratic function. We don't have any other strategy right now other than creating a table. Create a table at time 0. We know that's going to give us 30. That's our y-intercept. We substitute in 1. That's an easy one. 1 squared times -16. -16 plus 30 is 14. And we see even after 2 seconds, it has passed the ground level edge of the cliff, right? If we're going to say, hey, when does it actually hit the cliff? It's somewhere, according to this graph, somewhere just before 1.5 seconds. All right. Now, wouldn't it be interesting if there was some way that we could, given the equation of a parabola, determine when that parabola is going to hit the x-axis, which almost always means, in a gravity equation, when the object hits the ground. You might be saying, hey, Mr. Montoya, that's easy. If I just substitute in 0 for h, then I'll be able to calculate what t is, because when it hits the ground, h is 0. That's just the height, right? And then you just come back here, substitute 0 in for h, subtract 30 from both sides, divide both sides by -16, take the square root, and you're golden, right? You'll end up with a negative time and a positive time, and the negative time doesn't make sense, and the positive time will be somewhere around 1.5, right? And in this case, super easy. Once we end up with a bx, things get weird. Okay, so let's try your quick check. Suppose a squirrel is in a tree 24 feet above the ground. She drops an acorn. The function h equals -16 t squared plus 24. The only thing difference here is the 24, because it's 24 feet and not 30 feet. And like it was in the previous question, gives the height of the acorn in feet after t seconds. Graph this function. So here's the graph of the function. The only thing I'm missing, because I didn't spend a whole lot of time in Desmos adding labels, is the labels for the axes. So this axis is going to be h, or the height of the acorn. This axis is going to be time. And you'll see as time passes, it doesn't take but a little bit more than a second for that acorn to hit the ground. All right. So a reasonable domain and range for this function is very similar to what I'm showing you here. It doesn't make sense to show a lot of values of y less than 0 because y equals 0 represents the ground. So it stopped moving. It's hit the ground, right? And time, it doesn't make sense to show a whole lot more time after the object hits the ground unless there's something else going on where we need to know what the object is doing after it hits the ground. All right, and negative time doesn't make sense unless maybe the object was somehow hurled into the air and we needed to track that until it hit its vertex and then started falling down. And somehow, for some reason, we didn't want to start the time when the object got hurled into the air, right? You imagine, even if we said, all right, we put this acorn in a cannon and shot it up into the air, once we shot it, that would be our time 0. Then we wouldn't necessarily put that back in time. So oftentimes, if you're talking about gravity, you're looking at a range of positive values and a domain of positive values as well. All right, so now on to homework. So the homework is going to be assigned in Google Classroom. This is going to end the video. However, in this PowerPoint, you will see all of the pages for the homework. I'm figuring odds 1 through 33 should be fine for this section. All right, thanks for listening as long as you have. And even if it was on double speed, I hope you enjoyed it. See you guys soon. I hope all of this stuff passes over. We end up in class sooner rather than later. All right, have a good one.